Welcome to Lecture 12 of Vector101. Today we'll be talking about computing eigenvalues. On Monday we talked about what an eigenvalue is, and now we'll compute them. Before I begin, I have a short PSA, which is that this lecture will be shorter than usual, and going forward they will probably continue to be shorter. And that is because I am applying to grad school this summer, which takes a lot of time. And so does preparing these lectures takes a lot of time. So I kind of have to borrow some time from lecture prep to work on grad apps. So I apologize. I really don't want to have to do that, but I kind of have to. So anyway, apologies for that. I still hope that I can tell you a complete story, even if it is a little shorter. All right, and let me make sure I have the chat pulled up. Sorry about that. Okay, sorry, I think we're back. Okay, right, let's get on to computing eigenvalues. Or well, not quite, because the first thing we have to do is look at the demos from last week. So if anybody hung around to the very end of last lecture, or lecture 10, I had some demos for you and they broke. And I realized they broke because the row reduce code that we wrote must have had some issue with it. Maybe it's because we didn't do partial pivoting, and so there was some accumulation of error. I don't really know what the issue was, but I think that the code we wrote, unfortunately, caused the demos to break. So the correct code, the code that seems to work at least, is on the GitHub. And so now I will show you those demos again, and hopefully they will work this time. So let's switch on over to that. Borp says, we forgot to check if there were no rows with valid pivots to swap with. Oh gosh, did we just never swap rows? Oh, okay. That's embarrassing. All right. Make sure I'm switched over. Okay. So to remind you all, last week we talked about, well, we spent most of last week talking about the row reduce function, but at the very end, we talked about null space and what the fundamental spaces look like. So here's a visual that we saw in week 3, maybe. We were looking at linear transformations. And so once again, I'll show you that visual. So these green, red, and blue vectors here, these are the columns of a matrix, and they define how our linear transformation works. So it's a linear transformation that takes vectors from R3 and spits out a vector in R3. And so if I move this vector here, we can see that our space gets skewed. And well, I can do all sorts of things with this. I mean, I can rotate it and so on. So what we're looking at right now, this is the column space, which kind of makes sense. So these green, blue, and red, I said these are the columns of our matrix, and the column space is all of the linear combinations of these columns. And really what you're looking at right here, this box here, is only just a small subset of the column space. Really, the column space is all of R3. So you can get to any point in R3 by making combinations of these column vectors. So similarly, you can do the same thing for the row space. I mean, it's less obvious geometrically what we're looking at. I mean, we're looking at linear combinations of the rows, and again, the row space is really all of R3, but it's like tough to show that. So that's the row space and the column space. Now let's look at the left null space, and so okay, so it's been a while since we've talked about this. Well, okay, maybe we'll just kind of look at the pictures for now and get a geometric understanding for what things mean. So what's interesting to notice about the column space here, so the left null space is perpendicular to the column space. So what I did is I took that red vector and I crushed it to 0, meaning now the column space is only this plane spanned by these green and blue columns. And the left null space is this line that goes perpendicular to the plane. And what the left null space describes is it's like the direction we can't move in. So if we are a vector and we transform ourselves under our matrix and we land in this plane, the left null space tells us like the direction we cannot move. Because we are confined to this plane, we cannot move along the pink line. All right, so it follows a column space. And let's say I then crush this vector. Okay, so now the column space is only the span of the green vector, and the left null space is now two-dimensional. This is the entire plane of directions that we can no longer walk in. And then a similar thing happens for the row space and the null space. So the row space is now just this 1D line, and then the null space is perpendicular. Right. So let's remember what the null space is. The null space is every vector that gets sent to 0 under the linear transformation. So if I take this red vector here and I crush it so that it goes to 0, we now see that our null space is this line. So why does every point on this line get sent to 0? Well, every point on this line already had a y-coordinate of 0 and already had a z-coordinate of 0. So when we crushed the x-axis, what we did is we also sent the x-coordinate to 0. So now everything on this line gets sent to the 0 vector. And I can do the same thing again. So now I can crush this axis, and everything in this plane gets sent to 0 because everything on this plane already had a z-axis of 0. And then we crush the x and y axis, so now the whole thing goes to 0. And it doesn't have to look like this. We could also do this, and now our null space is this diagonal line. It's kind of like amusing, I think, to play around with this and sort of figure out why this is the null space. All right, do we have any questions about this? If the column space is the span of your basis vectors, what is the row space? The row space is it's the span of the row vectors. Alternatively, you could think about it as the column space of the transpose. I don't know if that actually is any clearer to call it that. So when we transpose a matrix, every column becomes a row and every row becomes a column. So the row space is the column space of the transpose. What are the implications of that? What does the row space represent? I don't have an answer for you. I will have to think about that and get back to you. Yeah, I'm not sure. Okay, Aiden's comment is the row space is not very useful. So, all right, now I don't feel too bad. All right, we'll switch back to the notes for eigenvectors. Okay. Now let's recap briefly what we did on Monday. And before we do that, of course, we have reminders to do the exercises and to come to office hours. All right, so a recap, we talked about the eigenvalue problem. And the eigenvalue problem is this. If you're given a square matrix, we want to find all of the non-zero scalars lambda such that ax equals lambda x. This is like a little hard to get your head around, I think. So what's interesting about this problem is that x is some vector such that when you multiply it by your matrix, all it does is it gets scaled. That's what lambda is. Lambda is the scale factor of this x vector. And so we want to find all such non-zero scale factors that have a solution to this equation. So what we're going to do to begin is, well, we're going to move some things around. So we're going to take this lambda x and we're going to move it to the left-hand side, and we'll get ax minus lambda x is 0. And then we notice that there is an x on the right side of the a and an x on the right side of the lambda. So we want to somehow factor out this x. But because a is a matrix and lambda is a scalar, it wouldn't make sense to just do a minus lambda x equals 0, because then we'd be subtracting a scalar from a matrix, which doesn't really make sense. So instead what we'll do is we'll put it in an equivalent form. So equivalently, this is ax minus lambda times the identity matrix times x equals 0. So this ix, this is just the identity matrix with 1s down the diagonal times x, and this just gives you back x. So this is why we can do this. All right, and then because ax is a matrix, because this a is a matrix, lambda I is a matrix, we can factor out this a to get a minus lambda I times x is 0. And so now this looks familiar because it looks like a null space problem. So what this is saying is that if we know lambda, so if we know some lambda that satisfies this, then we can solve for all of the x's. We can solve for all of the x's as the null space of a minus lambda I. So if we know some scale factor that makes this equation true, then it's not hard to find these vectors, because we already know how to compute the null space. Borb asks, so with the eigenvalue problem, we are trying to solve for scalars that carry out the same multiplication on x that a does. Yes, that's exactly right. I couldn't have said it any better. Right, so this is sort of the standard manipulation that we do to see that all of these x's are just in the null space of a minus lambda I. So getting the x's is not hard. What is hard is finding the lambdas, the eigenvalues. So this lambda, we call this an eigenvalue, and this x we call an eigenvector. And every eigenvector is associated to an eigenvalue. They come in pairs. Well, any eigenvalue has infinitely many eigenvectors, so that assignment is not unique. All right. I briefly want to talk about some terminology because I at least find it interesting. So according to the internet, the word eigen is German for own characteristic or proper. Uh, which to me is like what do these three words have in common? I have no idea. This like tells me nothing. This gets me no closer to understanding what eigen means. But so it goes. This is the word that we use. And so what we said an eigenvector is it's a vector that gets sent to a scaled version of itself by a linear transformation. And then an eigenvalue is the amount that eigenvector gets scaled by. So I should maybe note that this was our lambda, and this was our x. And then an eigenspace is we take all of the eigenvectors associated with an eigenvalue, and we chuck in the zero vector, and this forms, I claim it forms a subspace of Rn. So, all right. Let me show you some pictures. I think that will help. Sorry, I actually forgot to pull the pictures up. I'm really glad I left a note for myself. All right, let me switch my screen over to this one. And I also have to change the recording, one sec. Okay, so this first picture, so these two, I just got them from Wikipedia. I would have normally made these myself, but I was, well, yeah, scarce on time. So here's a linear transformation. We can see that it is skewing the Mona Lisa. And can anybody guess, like, give me an example of a vector that only gets scaled by this linear transformation? Like, what is an example of an eigenvector for this transformation? The y-axis. So the y-axis would not be an eigenvector because on the left-hand side we see this standard basis vector, or not necessarily, but it's just some vector on the y-axis. We see that it gets moved to the right by this linear transformation. So it doesn't only get scaled. Every eigenvector, when you push it through a linear transformation, it only gets scaled. So it'll be pointing in the same direction, but it might be, longer, shorter, it might point in the opposite direction. So this one, the y-axis wouldn't be an eigenvector, but what would be an eigenvector is the x-axis. You'll notice that that's right. Yeah, anything on the x-axis just stays put. And so it actually has an eigenvalue of 1 because the scale factor is just 1. It keeps its scale under this linear transformation. All right, now I'll show you this cool GIF. So this is showing kind of a family of linear transformations that's animated over time. And these red lines, these are the these are spans of eigenvectors. So every vector on this line, on these red lines, they only get scaled. They don't get knocked off their axis by the linear transformation. All right, are we good with these visuals? Okay, good. All right, let me switch back over to the notes. All right, so now we're going to talk about computing eigenvalues. And there are some like really terrible ways to compute eigenvalues, and then there's like a decent way, and then there are some much better ways. So today we're going to talk about what I think is a decent method for computing eigenvalues, which is the power method. And what's so great about the power method is its simplicity. Like this is on the order of Gram-Schmidt in terms of simplicity compared to like row reduce, which was a rough one. But this one's not going to be bad. All right. So what is the power method? So first of all, the power method on its own, in its naive form, does not give us every eigenvalue. It gives us only the largest eigenvalue of A. And then furthermore, it only works on certain matrices. So we're going to assume that our matrix, which is n by n, has n linearly independent eigenvectors. Maybe we should recall what linearly independent means. It means that any of these vectors in this list, any of these x1 through xn, they cannot be written as linear combinations of each other. So x1 could not equal some linear combination. I screwed up. Could not equal some linear combination like this. Like these would all have to be, yeah. Sorry. Okay. So it has n linearly independent eigenvectors, and then its eigenvalues. What's notable about its eigenvalues is that it has to have one eigenvalue that's larger than the rest. So if you notice these less than or equal to signs, what it means is that some of these n eigenvalues can be equal. So we don't have to have n distinct eigenvalues, but what we do have to have is one eigenvalue that's larger than the rest. And so this is the eigenvalue that we're going to compute. All right, let's go through the motivation of how you arrive at the power method. So we're going to start with some vector u, and this vector is going to be our initial guess. So we're going to start with well, let me back up. The first thing we're going to do with the power method is we're actually going to compute an eigenvector. Even though this is the eigenvalue problem, we're going to compute an eigenvector, and from this we'll get an eigenvalue. So this u here, this is our initial guess for an eigenvector. Okay, and because our eigenvectors are linearly independent, what we can do is we can write u as a linear combination of these vectors. So u is going to be some linear combination of these vectors where these c's are scalars. And then what we're going to do is we're going to suppose that u is not orthogonal to x1. Well, maybe it's not, I suppose it's not exactly clear why we need this yet, so let me keep going. So we've written u as this linear combination, and then we're going to hit it with a. We're going to multiply u by a, and well, let's substitute in what we have up here for u. So this is going to go in right there. And then we can distribute our a. And what you'll notice is that these ax1, remember, these x's are eigenvectors. So ax1, this is going to be lambda 1 x1. And similarly, this will work for all of the x's. So now we can just make this c1 lambda 1 x1 through cn lambda n xn. And so what's important about this comment here, this comment I made that u is not orthogonal to x1, is because it's not orthogonal, this c1 has to be non-zero. So like u is a non-zero amount in the direction of x1. Like u points in some amount in the direction of x1. And what's important there is that because the c1 is not zero, this whole term won't be zero. So our eigenvalue appears. That's the whole point. Okay, so maybe I should just say that this implies that c1 lambda 1 x1 is not zero, so that it appears somewhere in our equation. Okay. If that's clear, I'll keep moving on. All right. So what we're going to do is we're just going to do it again. We're going to hit u with a second time. So now we're going to have a squared times u. And well, what did we just compute? So this is going to be a times u, which we said was a times c1 lambda 1 x1 all the way through cn lambda n xn. And then we're going to do the same trick. So we're going to distribute that a again. So now this will be c1 lambda 1 a x1 all the way through cn lambda n a x to the n. And then again, this ax1, this is just lambda x1. And this axn is just lambda xn, or lambda n xn. So now we get c1 lambda 1 squared x1 through cn lambda n squared xn. So what's happening is that each time we multiply u times a, we're seeing these eigenvalues appear in the same power. So a squared times u, we get these eigenvalues squared. So then in general, if we multiply u by a k times, what we're going to get is c1 times lambda 1 to the k x1 plus dot 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 plus cn lambda n to the k xn. All right, and so over time, what happens is that we expect this, I think this should have been lambda 1. We expect lambda 1 to be the dominating eigenvalue. Actually, what should I say was the largest eigenvalue? I said lambda n is the largest eigenvalue. Okay, so this should have been an n. This should have been an n. And, okay, so over time we expect lambda n to be the largest eigenvalue. Well, lambda n will get really large, and it will eclipse all of these other guys. So then what we expect is that a to the k times u is approximately cn lambda n to the k xn, and then plus some smaller stuff. So lambda n, because it's the largest eigenvalue, you raise it to the power of k, and it's going to eclipse all of the small stuff, and so this is roughly equal. Is all of this? Are there any questions about this process? Okay. All right. That's totally fine. I think we have some extra time baked into today's schedule, so I'm fine going back and like where along this process did I lose you? Not really seeing the big picture. So all we're doing right now is we're just observing how eigenvalues and eigenvectors act. Like all we know, this is all we know. I think, sorry, my screen is, there we go. Right. This ax equals lambda x, this is all we know about eigenvalues and eigenvectors. And then we're just repeatedly using this fact to deduce some nice property that we can then use in our computation. So like I don't know, I wouldn't try to like see this in your head, of like a picture in your head. All we're doing is just using this algebraic fact. That's right. Yeah, we're just like deriving some properties about eigenvalues and eigenvectors. And specifically, if we make this assumption about our eigenvalues, that we have one that's larger than the rest, so we have this lambda n that's the largest eigenvalue, that if we repeatedly take some vector and multiply it by k, then this lambda n is going to stand out the most because it was the largest, and we raise it to a big power, is going to stand out. So we take u and we hit it with a k times, and then it's just going to be approximately this value, and everything else is going to be smaller, and it'll be so small that we won't care about it. That's kind of the highlight of it. How is that? That's a bit easier. Okay. So yeah, like specifically where we used our a x equals lambda x fact is right here. So we right, so we wrote u as a linear combination of our eigenvectors. So u, right, it's just some combination, and then we plug it in for here. Then we distribute a, and then we use our fact. We use this fact to get from ax1 and these axn to lambda 1 x1 and lambda n xn. And then on the next page, we just used our fact again. So we see these ax1 and axn, these appear again. And then again, these are just lambda 1 x1, lambda n xn. And we just keep doing it. We just repeatedly use this one fact over and over. All right. So this is our power method algorithm. And all we do is we start with some guess, some random vector. And like in general, if we just choose some random vector, it is very probable that it will be pointing in some amount in the direction of our eigenvector. Well, right. Anyway, yeah. So we're going to choose some random vector, and then we're just going to hit it with a again and again. So the k plus 1th step is to take the kth step and multiply it by a. And then you'll notice that this term down here. So what is this term doing? Well, this stops the lambda n to the k from growing or decaying exponentially. I'm not going to fit that exponentially. So this part here is like exactly what we just saw, is that at each step, all we do is we take our vector and we multiply it by a. And we multiply it by a and we keep doing it again and again. And then just for the sake of working with nice numbers, we always make sure that we normalize it so that it doesn't get too big or too small. But even though we normalize it, this vector is still going to point in the same direction as uk. So it's still going to be potentially an eigenvector. Looks kind of like induction. Yeah, I see that. It's kind of, well, it's like induction in the sense that you just do something over and over, but I wouldn't draw a strong comparison between them. Okay, so we hit it with A repeatedly, and then we need some condition for when do we stop. So we stop when our successive iterations get very close. And you could do this with like a magnitude check or something. All right, so now we're going to code this, and hopefully that'll help cement it in our brains. Okay, I think we can all see that. Okay. Before I get to coding this, maybe I should mention, so there's been some changes in our linear algebra library as usual, because I just added in the homework solutions from last week. So now in our linear algebra library, row reduce got swapped out with this system solver method or module, and row reduce is still there. Let me increase that font size. Row reduce is still there, but now we have some other functions which were part of the homework, computing the null space and counting the solutions to a linear system. So that's all that's changed there. And then I think I added a method to the matrix class. I think transpose might be new. Yeah, augment, just augment two matrices. Yeah, small changes. Won't really matter to us today, but I didn't want us to be confused. So today we're working on this eigensolver module. We're going to work on our power method. I suppose the very first thing that we should do is we should assert that our matrix is indeed a matrix. And we should also assert that it's a square matrix. All right, and then the next thing we do is we start with some random vector that's going to be our guess for the eigenvector, and then we iterate on this guess. I'm going to start with an eigenvector, and well, I guess we're going to need a table of random values. So how should we do this? I guess we'll do, so for each entry, we'll just set it to math.random. And then lastly, we'll make it a vector. So then eigenvector is going to be vector.new, and we'll give it vector. Okay, so now we have this is our initial guess. We start with some random vector, and then we're going to improve on this guess. So we're going to repeatedly do something. And, well, we'll get to our stop condition. So what we're going to do is, well, we're going to modify our eigenvector. So let's make sure that we don't lose track of the current state of the eigenvector. We'll just keep track of that there. And then we're going to update our eigenvector by taking our matrix and we multiply it by the current eigenvector, or our guess for the eigenvector, and then we unitize it or normalize it. So in our notes, this was U, and matrix was A, and we just repeatedly multiplied U by A. And then we normalize it so that our numbers don't go really huge or really small. And then we're going to keep doing this until our successive iterations get really close, and so we know that we're converging on a solution. So we're going to converge on a solution when the difference between, well, when the magnitude of the difference between our successive eigenvectors is less than some really small number. All right, and then to be safe, we should actually add one more thing. So what happens when this process just takes a really long time? Like, it takes a really long time to converge, and we don't want our computer to hang or something like this. Right, so what we should also keep track of is how many iterations we've performed and have a cap on the amount of iterations that we can do. So we'll start at 0 iterations and we'll increment this. And then if our iterations gets too large, like say 50, then we'll give up. It was converging too slowly. Okay, so at this point, we have what we think is a pretty good candidate for an eigenvector. And from this, we need to deduce the eigenvalue. Sorry, I'm looking at my notes, and I think it's nonsense. Okay, so here's what I have in my notes. So we're going to do the iteration one last time where we multiply by the matrix. And we're going to take the first coordinate and divide by the first coordinate of the previous. What am I doing here? I think what I'm doing is that I'm solving for lambda by, that's right, okay. So I'm taking the first coordinate of this and the first coordinate of this, and then dividing one to the other side to solve for lambda. Right, the question is, so we can't solve for the eigenvector exactly. I mean, you can. I mean, you can solve for it within a certain level of tolerance. Like you could set your tolerance to be really, really low. And it's like effectively just good enough. I mean, you probably, so, okay. The answer to your question is that yes, like this, what we're doing is we're implementing an iterative method, but there are non-iterative methods and there are, yeah. So like if you open up Mathematica, you could solve for an eigenvalue symbolically and it would give you an exact solution. I guess so, right. So earlier I had said that there are some terrible ways to solve for eigenvalues. And the terrible way is not iterative. It's extremely slow. And probably as you're doing it, you would build up so much error that you wouldn't even know if your solution was correct. But a symbolic solver, I guess in theory, could do it that way. Okay. Yeah, let me move this comment up there. And we'll return our eigenvalue and we'll return our eigenvector. Yeah, I think that's right. Yeah, it would be pretty terrible to do it without an iterative method. And actually, so yeah, so this iterative method we're doing is a decent way, but so is that true? Uh, I wanted to claim that the best method is iterative. I actually don't recall. All right, we should probably make sure that this works. So let's construct some matrix. And yeah, okay. So I'm going to construct a matrix whose eigenvalues I already know. And then we're going to feed this into our eigensolver. So let's print linear algebra eigensolver power method, feed in our matrix, and see what we get. Sorry, I'm looking for the command line button. Oh my god, which of these tiny buttons is it? We'll just run it. Oh goodness. Oh, that's strange. So we're doing a, oh, okay. We're trying to do a matrix vector multiply. And I was pretty sure that I added that. Okay, I don't see it in this version of the notes. Yeah. Uh, yeah. I thought that I had added that. I guess not. All right, I have some more notes that I want to get through, but we can snap our fingers and say ta-da, and it it works. Okay, sorry about that. Yeah, this is a really good question, Borb. So Borb asks, now that we can calculate eigenvalues and eigenvectors, what are they used for? And the answer is like everything. It's kind of like a satisfying answer and not a satisfying answer. Like not at all. Like when we discussed linear transformations, we said that linear transformations are like the most important function in applied math because they're used like literally everywhere in physics, economics, computational biology, and chemistry. Like everybody needs to solve linear systems of equations, and so everybody needs linear transformations. And it's the same goes for eigenvalues and eigenvectors. Like everybody, this is just a core component of doing linear algebra. Um, that said, like what's a concrete example of where we need this? Well, yeah, I thought for a while about what example to give in lecture, and ultimately I didn't settle on a good one because every kind of basic example of where you could use an eigenvalue is kind of like hard to reach. Like the basic examples are, we would need some, for the one I'm thinking of, we would need a little bit of calculus. Yeah. Okay. I'll have to get back to you on a good example. Here's an example. How do you know the axis of rotation of a C frame? So the axis of rotation of a C frame is going to be an eigenvector because that axis doesn't change at all. It doesn't even get scaled. So it actually has an eigenvalue of 1. So there's one example that we kind of understand. It's not very useful. It's not a good question. It's not a good answer to your question. I apologize. Um, but let me move on for now. So there's various improvements that we can make on our power method. One of them that I thought we'd have time to implement, but unfortunately not. One of them is the block power method. And what this does is instead of computing one eigenvector or one eigenvalue, it computes uh, p eigenvalues where p can be up to n. So we can use this to compute all of our eigenvalues. And well, I guess I won't go through it now, but we do this using Gram-Schmidt. So we start with some, I guess I will go through it. We'll start with some orthonormal vectors, and we do the exact same thing. We just multiply it by a. And then after each step, we orthonormalize them again using Gram-Schmidt. Or do we orthonormalize? Yeah, that's right. We orthonormalize using Gram-Schmidt to make sure that they're all orthonormal, and then we keep doing the recurrence relation. and this gives us p eigenvalues simultaneously. Okay, the last thing I want to talk about is Francis's algorithm. Francis's algorithm, this is like the actual algorithm that people use to compute eigenvalues because it's really good. It converges quickly. And what's also interesting is that it uses Gram-Schmidt. So there's another place where Gram-Schmidt, the GOAT, shows up again to save the day. I won't actually tell you how Francis's algorithm works, but it has an interesting story to it. So it was invented by this guy, John Francis, in the 50s. And John Francis was he was just some dude. Like some dude who liked math. He wasn't like a mathematician per se. I mean, he was working in industry, and I've actually stolen some slides from another professor. He was right. So he worked on this in the 50s. What he was doing was some sort of analysis on plane engines, I think, or something to do with planes. And so he was tasked with writing these routines, these linear algebra routines, and he got really fixated on the eigenvalue routine. Sort of his manager tolerated him working on this because, well, yeah, there was already a method at the time that was pretty good, but he kept working on it, and eventually invented his own, and then he just moved on to other things. So he invented this really amazing algorithm that somebody said is one of the top 10 algorithms of the 20th century, and then just moved on with his life. So where is he now? Well, as of the creation of this PowerPoint that I stole, he was still alive. I don't know. I don't know when this was made. And what's really interesting is that he didn't even know that anybody used his algorithm until 2007. So he invented this in the late 50s and then finds out over 50 years later that he created this a wonderful algorithm. And so finally they got him out of the woodworks and asked him to give a talk in 2009. Yeah, so there's John Francis. Right. Yeah. All right. I think we'll end lecture there for today. Thanks for sticking around a few minutes after, and I'll hang around for questions.